Hello class, let's discuss statical stability of floating bodies. So we can say that floating body is stable when an external force being applied on the floating body, and when it is removed, the the floating body will return to its original position, or it will return to equilibrium. So on the other hand, if the floating body will move on the new equilibrium, or it will not return to its original position, so we can say that that body is unstable. So how can we determine if the body is stable or it is unstable? So first, let's start here when the body is in the upright position. So the present forces here on this floating body are the weight of the body, which is acting on the center of gravity of the body, and we have the upward force, which is the buoyant force, which is acting on the center of buoyancy, or BO, and we have here point M. So what's this point M here? So that's what we call the metacenter. It is the point on the vertical neutral axis through which the buoyant force always acts for a small angle of tilt. So in an upright position, we call that as the point, or the initial value, or initial position of the metacenter. So to locate the metacenter, uh, we compute the metacentric height. So the metacentric height is mg, or the distance from that metacenter to the center of gravity of the body. So the metacentric height is equals to mbo, or the distance from metacenter to the center of buoyancy, plus or minus gbo, or the distance between the center of gravity of the body and the center of buoyancy. So positive if G is above the center of buoyancy, and negative if G, or the center of gravity of the body, is below the center of buoyancy. So to determine the initial value of MBO, or the distance from the metacenter to the center of buoyancy, we can compute that as the ratio of the moment of inertia divided by the volume displaced. For the moment of inertia, we will take into consider here the axis in which the body might overturn. So we have two directions of axis here, this axis and this axis, where the body might overturn on this axis. Let's say this is a y-axis, and on this direction the body might overturn this direction on the x-axis. So what axis are we going to use here in considering the value for the moment of inertia? So let's say we have the dimensions of the body here, which is the width and the length. We also have the depth. So in computing the moment of inertia, we will only consider here the width and the length of this body. So let's say this area only. So in determining the moment of inertia, we have two moment of inertias, either on this axis y. Okay, let's say iy. So in iy, if this is the axis that we will consider in determining the centroidal moment of inertia, we have ph cubed over 12. So our B will serve, L will serve as B, and H is the B. So LB cubed over 12. On the other hand, if we consider the x-axis, we have BH cubed over 12 again. This will serve as the base, which is parallel to the x-axis. B and H is this distance, L cubed over 12. So now we will compare what moment of inertia will give us the lesser value of moment of inertia, either on the x-axis or the y-axis. So the higher the value of moment of inertia, the more stable it is on that axis. So based on the solution where L, this dimension L is the length, which is the longer dimension, so if that value will be raised to 3, it will give us a greater value for the moment of inertia compared to this B with B when it is raised to 3. So the moment of inertia that we are going to use here is this solution. So in rectangular prism, we will use the solution in the moment of inertia for the initial value of MPO. So just to exaggerate, okay class, just to exaggerate the figure, okay, we have a wooden block here with a length and P. So if I consider this axis IY, so there is a tendency that this wooden block will overturn on this direction. It is easier to overturn this wooden block in this direction on the y-axis as compared to this direction where we have x-axis. So it is harder for this block to be overturned on the x-axis because it is more stable on this axis compared to the y-axis. It is lesser stable because it gives us the lesser value of the moment of inertia. Okay, when the body is in a tilting position, it is said to be stable when that position of the metacenter is right above the center of gravity. So as you can see here, the point of metacenter is still in line because it's the same axis with the center of buoyancy and center of gravity. So again, point M is the point at which the buoyant force, the direction of the buoyant force goes. Okay, so since it is in the tilted position already, so we will have a new position of the point at which the buoyant force is acting. So we just put a symbol BO prime here for the new position of the center of buoyancy of our of the buoyant force. So again, this BO here, that's the initial position of the buoyant force, and this BO prime here is our new center of buoyancy of the buoyant force. Okay, so it is stable when the metacenter is above the center of gravity. So again, same value for the weight and the buoyant force. So it is said to be unstable if the metacenter is below the center of gravity. So again, this is our buoyant force here. This point is BO prime, the new position of the center of buoyancy. So the buoyant force is directing towards point M. So point M is below G. So what will happen here if it is stable is that it will move into a new equilibrium. It will overturn and it will find another position that will make it stable for this floating body. Okay. So how do we compute the righting moment and the overturning moment? So righting moment if it is stable, overturning moment if it is unstable, if the floating body is unstable. So we can compute the righting moment or the overturning moment simply by taking the moment at point M, okay, at the meta center. So if we take the moment at the meta center, the forces or the force present here is just the weight of the object, and just take the horizontal distance from point G to this line here. Okay, so this distance is your distance x. So to compute this distance x here, so just take this right triangle here. So this distance here from point G to point M, that's mg. And if we have the angle of tilt theta, so just take the trigonometric function, sine function, and we will come up to the value of x, which is mg sine theta. Okay, so to locate the metacentric height or the mg, we should compute first the MBO, or the distance from the metacenter to the initial point of center of buoyancy of the body. So we have a general formula of Vs over Vd sine theta. So this V here, okay, this V here is the volume of the wedge that is submerged on the fluid, as well as the volume of the wedge on the other side is the one that is reduced. Okay, so it means this volume here, this triangular volume here, okay, triangular prism, if it is rectangular, that will be your volume of the wedge. Okay, so since it is symmetrical, the volume of wedge here is just the same. So this V, just determine the volume of the wedge on one side only, because they are just the same. Okay, just one side. So that's the volume of wedge that is being submerged to. So Vd is the volume displaced or the volume submerged. So the volume submerged Vd is just the same as the volume displaced at the initial position, because this volume of the wedge submerged here, which is an additional volume, is just the same as the volume that is reduced when it tilts. So they just cancel out each other. So it means the volume displaced at the original position is just the same when it is in the tilt position. So that's your volume displaced sine theta, or theta is just the angle of tilt. Okay, for distance s, that distance s here is just the horizontal distance between the centroid of each wedge. So again, if this is your wedge on each end, just locate the centroid and take the horizontal distance between the two centroids. Okay, and that's your S. Same solution applies in determining the metacentric height. Mg equals to MBO plus or minus GBO. So if we have a rectangular section or a rectangular prism that is a floating body, so we can directly use this solution right here, which is just derived from our general solution. Okay, so that we will not solve the wedges. We can directly solve this. We can directly solve this MBO right here. So we have a formula of b squared over 12d times 1 plus tan squared theta over 2. So b is the width of the body, d is the depth of fluid at the initial position. Okay, so that's it. Let's now solve some sample problems. Sample number 1, a rectangular skull, 10 meters wide, 15 meters long, 4 meters high, has a drop in seawater of 3 meters. Its center of gravity is 2.5 meters above the bottom of the skull. So determine the initial metacentric height, then the righting or overturning moment when the skull tilts until one side is just at the point of submergence. So first, let's write down the given. We have 10-meter width. So if this is the figure, 10 meters width, 15 meters in length, dimension here, and we have 4 meters height of the rectangular skull. So the draft in sea water is 3 meters. Okay. Its center of gravity is 2.5 meters above. So in this problem, it is indicated here the location of the center of gravity. So just follow that. That's 2.5 somewhere here. Your point G. That's 2.5 meters above the sky. Determine the metacentric height, the initial metacentric height. So for letter A, we have mg is equals to MBO plus or minus GBO. So determine first MBO. We have a solution of, for the initial metacentric height, that's the MBO is I over volume displaced. Again, this is your seawater surface. Okay, so I for the moment of inertia. So our moment, the area of concern here is this area right here, where we will consider here the axis that will give us a smaller value of moment of inertia. So on that axis will be our reference axis where the body will overturn, and it is perpendicular to the dimension or to the least dimension of the body, which is the width. Okay, so it is on this direction. So we have the moment of inertia of if this is B, this is L, which is 15 meters, we have LB cube over 12. So substitute L 15 meters, B is 10 raised to 3 over 12. So the moment of inertia is 15 times L cube over 12, 1 to 50. It's 1 to 50 meter raised to 4. Then we can now solve the moment MBO. So the volume displaced is equals to this volume right here, the volume submerged. So just find the area and multiply the length. So For the volume displaced, let me write it here. The volume displaced is just equals to 3 meters by 10 by 15. So the volume displaced is equals to 3 times 10 times 15, 450 cubic meters. Substitute 1 to 50, meter is to 4 over 450. The answer is 50. 2.78. 2.778. That's MBO, 2.778 meters. That's the answer. To find the metacentric height, okay, we have to locate first the centroidal center of gravity as well as the center of buoyancy. Okay, so on the given we have 2.5. The center of gravity is 2.5 above the bottom of the skull. For the center of buoyancy, we will just locate the centroid of the submerged part of this skull, which is this one. This is 3 meters, and the centroid of the submerged area here is on this point, which has a distance of 1.5 meters. So that's your BO. Now we have computed already MBO, so we will just measure 2.778 above BO. So just to compare, this distance right here between G and BO, we have 2.5 and 1.5. So the distance between the two is just 1 meter. And then let's locate the metacenter M, which is 2.778 above BO, okay, to measure MBO. So from BO going up, that's 2.778. Okay, so let's redraw that here. We have G, BO right here, and let's draw 2.778. Okay, so this is 1.5. This is 1.5. This is 1 meter. 2.778 is slightly above the skull. Okay, we just measure 2.778. It's right here. Your M, 2.778 meters. So that's your MBO. So M is above G. So we can say that my inspection here, MG is just equals to MBO. MBO is subtracted by GBO. So MBO is 2.778 minus GBO is 1 meter. MG equals to 1.778. So that's your initial metacentric height. Okay, this is the initial metacentric height. For overturning moment, when the skull tilts until one side is just at the point of submergence. Okay, so it means it is in the tilt position, which the skull tilts just at the point of submergence. So let's draw the figure. So here's the figure. it means that one corner is already submerged on the liquid surface. So we are required to determine the writing moment. What will be the writing moment? So we cannot determine the writing moment if we don't locate first the metacenter on the tilt position. So let's determine first the metacenter. So since this is a rectangular section, we can use the solution in locating the metacenter. We can use the solution for MBO, that is equals to b squared over 12d divided by 1 plus tangent squared theta over 2. But we don't have yet the value for the angle of tilt. So let's determine first the angle of tilt. So the angle of tilt can be determined by the triangle formed by the wedge shear. So we can already determine that distance, because if this is 4 meters and at the initial position this is the total depth is 4 meters, the depth of seawater is 3 meters, this is 1 meters. And taking the half of the width, which is 10 meters, that's 5 meters. So it means this distance right here is 5 meters. This is 1 meter. So let's compute the theta. Theta using tangent function. That's opposite 1 meter over hypotenuse 5. So theta equals to arc tangent of 1 meter over 5 meter. So that's arc tangent of 1 over 5. 11.3099 degrees. So substitute that here. We have depth of 3 meters. So D is 10. Okay. Substitute the values. MBO equals to 10 squared over 12 d 3 meters multiplied by 1 plus tangent squared of 11.3099 degrees to be divided by 2. So let's directly solve this. That's 10 squared over 12 times 3 multiplied by 1 plus tangent 11.3099 squared over 2. Okay, that's 2.8333 meters. So we have now MBO. So if the location of the center of buoyancy is measured 1.5 meters from the bottom, so this is 1.5. Okay, we measure 2.833 from center of buoyancy to locate point M. Okay, so 2 point something. Right here, that's your point M for the metacenter. Okay, so that's your metacenter point M here. So it means if we have a buoyant force, the buoyant force is just below that metacenter. So say right here. Okay. So that angle is the same as the angle of tilt. So this is your new location for the center of buoyancy. This is your buoyant force. Okay. So this is measured 2.833 meters. So the metacentric height mg equals to mbo plus or minus gbo. So we can say that from the figure, the metacenter is above the center of gravity, because center of gravity is 2.5 meters above from the bottom. So MBO is 2.833. So if it is above, we subtract. Okay. So subtract GBO. So just based on the figure, we have BO, G, M. So we computed MBO. So when you subtract GB, what remains is the metacentric height, mg. Now GBO is 1 meter. Okay, that's 1 meter. So 1 meter. So mg equals to 1.833 meters, or 8333. That's your metacentric height. So that's the new location, or the new metacentric height on the tilt position. So what is required here is the righting moment, or the overturning moment. So for the overturning moment, you determine this distance x here, the horizontal distance x, because we are taking the moment at m. If we take the moment at m, okay, we need what we need is the weight of the body and its perpendicular distance from point M. Okay, so that x depth from the slides that I've shown before, we have here the righting moment. Okay, this is righting moment because it is stable. It will just return to its original position. So that's W x, or W mg sine theta. So righting moment is equals to the weight of the object. W mg is 1.833 sine theta 11.3099 degrees. So the righting moment is equals to W. So 1.833 sine 11.3099. That's 0.3595. So meters. So what's the value for the weight? That's W. We can solve W by going back at the initial position. We take the sum of the vertical forces because we have W and the buoyant force. So since it is floating, when we take the sum of the vertical forces, we can say that the weight of the object is just equals to the buoyant force. So to solve for W, when we take the sum of the forces along the vertical, the weight of the object, say downward positive, the weight of the object is subtracted by the buoyant force equals to 0, or the weight is equals to buoyant force. So the buoyant force therefore is, since this is seawater seawater. Let's solve the buoyant force. The buoyant force is unit weight times volume. Since this is seawater, that's 9.81 kilonewtons per cubic meter multiplied by the specific gravity of seawater. That's 1.03. For the volume submerged, the volume displaced. Okay, we already solved that. That's 3 by 10 by 15 or 450 cubic meters. So that's 450 cubic meters. So the buoyant force, which is also the weight of the body, is equals to 4,546.935 kilonewtons. Okay, so substitute that now here on the writing moment. That's 4,546.935 times 0.3595 meters. That's kilonewtons. The writing moment is equals to 0.3595 1,634.623 kilonewton meter. Okay. So that's the writing moment. That's it. So you solve this problem right here. Okay. So you can also try class solving for the MBO using the general solution. Okay. In the general solution for MBO, we have Vs over Vd sine theta. Okay, you can solve those.